Yeah, so you'll be telling us about things that are not closed under factoring.
Okay, hello, this thing is on. It's a Goldilocks zone of volume, I hope. Okay, sounds good. So, sorry? Some streaming problem?
Did not change it from Zoom.
On Zoom, the camera is switched to audio. Now.
Okay. Yeah, so my name is Magnus. Very honored to give this talk on the Constitution Day of all days, so that's really nice. And I'll be talking about this paper on the closure properties of read-once algebraic branching programs, which was in collaboration with Robert Andrews, Jules Lamont, Pratik Vivedi, Nutan Limay, Srikant Srinivasan, and Sebastian Savana. So maybe I should just start with the big summary. Oh, there we go. And we've already seen much of this today, right? We've seen that. So on the left here we have the various models and the class, and we can see here which operations, algebraic operations, they're closed under. So we've seen for factoring we have algebraic circuits, algebraic branching programs, and now just recently algebraic formulas and constant depth circuits. So that's some really nice results. And for symmetric compositions, here we mean a Blaise-Gendel type result. So composition with the elementary symmetric polynomials. And we have the original one for algebraic circuits. The one for algebraic branching programs, at least one direction is true. I'm actually not sure about the other direction, but yeah, maybe take that with a grain of salt or do some digging. But for formulas and constant depth circuits, this is also true. So what we show in this paper is that, well, for read-once algebraic branching programs, all of these things are not. None of these are closed under this class. Not even powering. So it shows a stark weakness in this model, and it sort of reflects sparse polynomials, and we'll get into why that is. So just some notations. We will be working over the complex numbers, so I don't make any weird mistakes. And we have these shorthand notations, which you're probably familiar with. So before, maybe we should define what an roABP even is, for those who don't know. So let's start with an ABP. So this is an acyclic directed graph with a unique source and sink, such that with edges labeled with linear forms. And this ABP computes a polynomial by taking each path, multiplying all the edges, and summing over all such paths, right? And you're probably familiar with this. And we should think of this ABP as being layered, so the edges connecting layer I to I plus 1, because then we can define various ways to check the complexity of this. We have depth, which is the number of layers. The width, which is the maximal number of vertices throughout the layers. And the size, which is the total number of vertices. So here we have 3 examples of this easy linear form. First elementary symmetric polynomial. You can see here on the left, we can just do multiple edges, or we could, because we're allowed to, we can just do one edge, right? So that's also the reason why we do this. Or we could do it in this way more complicated way, which you may know why I've written this one. But before that, let's look at read-once Oblivious algebraic branching programs. So these are ABPs, but where the edges connecting layer I to I plus 1 are labeled by univariate polynomials of x pi I. So this pi here is a permutation, so that dictates which order we are reading the variables in. So you can only read the variable once as you go along a path, and then you can never read it again. And here we also have some complexity measures, so you can look at the width, which is again just the maximal number of vertices throughout the graph. The notion of depth we don't really care because that's just the number of variables. And the notion of size we also don't really care because that's bounded by the depth times the width. Alright, so looking back at our example, we had the first one here. This is not an roABP because we're mixing and matching all kinds of different variables. The second one here is also not an roABP because, well, it's not a univariate polynomial. But the third one here is. And you can see here that this has width too. So measuring the complexity of a polynomial with the in the roABP model, we focus on this width. So we say that the width of a polynomial in some fixed order, this is the smallest roABP which can compute, which computes f in this order. Smallest by width, I mean. But we can also talk about any order width, and this is just taking the minimum of all of these width over all kinds of permutations. And both of these here are bounded by sparsity, because you can, for each monomial, you can just create one disjoint path. Okay. So looking back at our results more formally, what we managed to show is that, well, there is some polynomial f which factors into this g and h, where f here is easy to compute compared to the factor g. So this shows that roABP is not closed under factoring. And then for the Blaise-Gel type result, we show that this cannot. There is no such result. We have some f which is really hard, where its symmetric counterpart is easy, and even in the reverse order we have examples of the symmetric polynomial where its regular counterpart is, or where the symmetric polynomial is hard but the regular counterpart is easy. Right. So why do we care about this? Well, maybe you ask, why do we care about roABP? And it's not just some kind of toy model, because we can actually compute a lot of different very interesting polynomials, like the elementary symmetric polynomials or the iterated matrix multiplication polynomial. So it can compute a bunch of interesting things. It's also very easy to analyze. We have this perfect characterization of roABP, or of the width of polynomials. We'll see this in a bit. And then, I'm not the expert on this, but apparently we understand everything about border complexity, and so there's been a lot of research in PIT within the roABP world. So specifically, our results, well, these are closure results, which should be interesting to everybody. I mean, you want to know what can you do within the model and not sort of get thrown out of the complexity class you're looking at. And closure results also play a vital role in various hardness randomness trade-off and the analyzing of GCT and resultants, like we saw before. So I'm going to be showing you the proof of non-closure under factoring. I'm going to be focusing on this, and then I'm going to be flashing you the symmetric compositions, the polynomials that we're interested in that case. So before we go to the concrete proof, let's look at this Nissan matrix. So this has also different names: coefficient matrix and partial derivative matrix. In Danish we say beloved child has many names. So but this Nissan matrix is based on a polynomial f, where you partition the two variables into two disjoint sets, and then you index the rows by monomials in the one partition and the columns by the other partition. And then the entries are given by the coefficient when you multiply these two monomials together. And what Nissan managed to show in 1991, I believe, is that if we take the partition dictated by the order that we're given, then actually the width, the fixed order width of this is exactly, or it's lower bounded by the rank, and if we take the max overall sinus cuts of this, then it's actually equality. And this is a really nice characterization, which makes it very computable, this roABP, which is why it's always the first example you go for when there's something new to look at. So let's look at an example. Here we have an invariant polynomial, which is huge and complex in some way. Some models might say it's complex, but it actually has width 1 in any order. And why is that? Well, we just take the straight line and then label the edges dictated by the order that we're given. But what if we tweak it just a tiny bit? So now we're substituting xi for yi zi. So we get this. It's basically the same polynomial, but now we just have two variables, right? And then let's say we take our order to be such that the partition is split into y and z. So here we just take, if you remember before the Hansen matrix, we just take I to be 1/2, and then everything left of that is y, everything right of that is z. Well, then the rank is huge. Then the rank is d to the n, which is the same as sparsity, so therefore the width is also d to the n. Exactly. And why is this? Well, we take the coefficient of yi zi. This is always non-zero because you can just plug out any such power vector. You just plug out the ones you want from each vector. If you have yi zj, where these are different, then this is 0 because z and j always come paired up. And so therefore our Hansen matrix is a permutation matrix, and so the rank is full, which is the cardinality of the I, which is d to the n. So this is sort of, this is, the width is the same as the sparsity, so let's take a look at this, the non-closure factoring for sparse polynomials. What goes wrong there? So the problem is really this devilish little polynomial, which if you've ever worked with sparse polynomials, you probably hate this guy. Because he factors into, we have a constant size polynomial, or a constant sparsity polynomial, which factors into this linear size, like it's very, very dense. It has very, very dense factor. And we can even construct the multivariate one by just multiplying with all the different variables. And now you might recognize this g here, right? This is the one we saw in example 1 before. So, sparsity are these things. So this g1 we saw before, so maybe we can lift it using the same trick as before, and indeed that's what we do. So if we do this variable substitution as before, then we get f over here. So yeah, we have the g over here, this is, as we recall, d to the n, and f over here, just by sparsity bound, this is 2 to the n. So that actually gives us the result we wanted, but this is only for fixed order. So it's very easy, but only for fixed order. So the question is, can we lift this even further to any order roABP? And the answer is yes, but now we have to be a little more careful and a little more creative. We have to use expander graphs. So I'm not really going to tell you what expander graphs are, but we only need one lemma, which concerns induced matchings. So an induced matching is a set of disjoint edges such that the graph induced by the endpoints of these edges is just the set you had before. So just a quick example you can see here on the left. If we take in the square here the north and south edge, this is not an induced matching because the graph induced by the endpoints of these two is the entire thing, right? But on the right here, this is an induced matching, so that's all good. And so what the lemma we want to use here, the induced matching lemma says, is that there actually exists a graph, Gn, on n vertices such that if you partition the vertices into two fairly equal-sized parts, then there is an induced matching of size omega n between these two partitions. Okay. And I'm not really going to tell you too much about the graph, but there are explicit constructions. These come from Ringel, Vathan, and Victorson. I believe it's with the zigzag product. They construct these. And then you can apply the expander mixing lemma. Okay. So how do we use this for the construction? Well, let's take this graph that was promised to us by the previous slide. Then what we do is that we take the polynomial as before, but now we're multiplying through by the, or we're indexing over the edges of this graph. So as before, we have sparsity bounded on f. This is bounded by 2 to the number of edges, which is 2 to the order of n. And so what remains to be shown is that this g here is still as hard as it was before, or roughly as hard as it was before. Okay. So just to reiterate, this is what we want to show, and once we've shown this, we're done, right? Because then we have our result. So how do we prove this? Well, let's take some permutation, any arbitrary permutation. This dictates a partitioning of our variables into these two. Let's just take them as the equalized sets. And of course, this partition of the variables induces a partition of the vertices. In much the same way, just take the index, right? And so by the induced matching lemma, we can see here that we have a matching between these two sets of vertices of cardinality omega n. And so now we just set the vertices which are not in this matching, we set these to 0 in G, which is just a partial, this is just a partial evaluation, and so this gives us this polynomial G tilde. So, it's basically the same as before, but now we're just taking the product over the edges in this matching. And because the induced matching lemma told us, well, one edge or one vertex is in one partition and the other vertex is in the other partition, you see here that xi is in y and xj is in z. So we can just relabel, and now you might recognize this looks exactly like the fixed order roABP case, and indeed we take the width. This is because pi was arbitrary, we have this equality. And this is lower bounded by partially evaluating. And because this is just the same as the fixed order case, we get this equality of cardinality. Yep. And by the induced matching lemma, we get our lower bound. So that's actually the entire proof, which is quite neat and tidy. It really shows how, the main thing is that we just lift this counterexample from the sparsity world to the roABP world using such an expander graph gadget type thing. So it's not too bad. I guess I have some time left, so I'm gonna be showing you the counterexamples for the Lagrangian delta type result. Oh yeah, maybe first talk about the fundamental theorem of symmetric polynomials, which you've probably seen, so I'll go quickly. We have some group acting on our set of variables, and then this induces an action on our polynomials through this equality. And if it stays the same, we call it G invariant. So if this doesn't change polynomial, it's G invariant. This actually gives us an algebra, f x to the g here. This is the algebra of G invariant polynomials. And what the fundamental theorem of symmetric polynomials then says is that, well, if we pick G to be Sn acting in the most obvious way you could think of, well, then this algebra is actually generated by the elementary symmetric polynomials. And we call these polynomials symmetric, the polynomials of this algebra. And so the way you should think of this theorem, at least in this talk, is that, well, if you have some symmetric polynomial, then this theorem says that there exists a unique polynomial f such that when evaluated at elementary symmetric polynomials, this gives you back the symmetric polynomial. And now what we ask is, what is the complexity relation between f of x and f sim of x? And in the first direction, we we show that there is an f such that f is very hard to compute, but the symmetric counterpart is very easy. And the polynomial we use is this product of a sum over some primitive roots. When you evaluate this, you get this quite nice sum of elementary symmetric polynomials at powers of xi. And then you can show that the width is 2 to the k half, and then you pick k appropriately and you get your result. One thing to note about this is that f of x here is actually the determinant of a particular circulant matrix. So this actually pops up a lot. I mean, the circulant matrix has its own Wikipedia page, so this might be of independent interest in some way. At least this polynomial pops up quite a bit. And in the other direction, we have a polynomial f, which is quite easy to compute, but once you evaluate it at the elementary symmetric polynomials, it becomes very difficult. And this example is, yeah, it's very easy. I mean, you just take xd to the k, this gives you ed to the k, and then width of this is this binomial coefficient or multinomial coefficient. And you pick k and d appropriately again. By the way, all these widths are analyzed, I mean, very standard ways with evaluation dimension. Yeah, this result also shows non-closure on the powering. You can also show non-closure on the powering using the same induced matching lemma as before. So there's 2 ways to do that. Okay, I'm going to be leaving you with some open problems. There are 3 open problems we have in the paper. And it turns out one of this, maybe I draw your attention to the second one, which has been solved in the affirmative, allegedly. It hasn't been published yet, so yeah, wait and see. But this problem is whether or not we can actually do this lifting thing in the general case. Because in the case that we did it, I mean, polynomials was very nicely structured such that you took factors of univariate polynomials, or took the product over univariate polynomials, which allowed us to do this, the trick we did here. But actually you can allegedly do this in a much more general way. Other than that, you know, can we get an exponential separation for this factoring result? And is there like the reverse of the powering? This is like, what about the root? Is that easy or hard? Yeah, so I think that's it.
Yeah, questions? Yeah, there's a question there.
Was there a reason you needed the counterexamples to be explicit? If you take random graphs, does that still work?
I guess random graphs should work, right? But I mean, it's always nice to have an explicit construction. Yeah.
Thanks.
So the next question asks about roABP series, right?
Yeah.
And so it's actually equivalent to understanding the partial derivative measure of power of polynomial compared to that of polynomial.
Sorry?
So it's equivalent to understanding the partial derivative measure of a power of a polynomial compared to that of the polynomial itself.
Ooh. Yeah. I get an affirmative from all things. Yeah. Yeah.
You know, so this was asked in different contexts as well.
Yeah. Mm. Yeah.
Yeah, okay. So if there are no more questions, let's thank Magnus again.